Let's solve a problem involving an LCR series circuit. We need to find the capacitance value that gives us unity power factor, and then calculate the circuit's Q factor. Here's our circuit. We have a resistor of 10 ohms, an inductor of 200 millihenries, and a capacitor connected in series to a 220 volt, 50 Hz AC source. For unity power factor, we know the circuit must be at resonance. At resonance, the inductive reactance X_L equals the capacitive reactance X_C. Let's first calculate the inductive reactance. X_L equals 2 pi FL. Plugging in our values, we get 2 pi times 50 Hz times 0.2 henries, which equals 20 pi ohms. Since we're at resonance, the capacitive reactance must also equal 20 pi ohms. We know that X_C equals 1 over 2 pi FC. Solving for C, we get C equals 1 over 2 pi F X_C. Plugging in our values, we get C equals 1 over 2 pi times 50 times 20 pi, which simplifies to 5.07 microfarads. Now for the Q factor. The Q factor equals 1 over R times the square root of L over C. Plugging in our values and calculating, we get a Q factor of approximately 19.87. To summarize, for unity power factor in our LCR circuit, we need a capacitance of 5.07 microfarads, and this gives us a Q factor of 19.87. Let's solve this Young's double-slit experiment problem. We need to find the wavelength of light used, given some information about the fringe pattern. Let's first visualize the experimental setup. We have a light source, then two slits separated by a distance d of 0.5 millimeters, and a screen placed 1 meter away. On the screen, we observe a pattern of bright and dark fringes. The problem tells us that the fifth bright fringe is 4.13 millimeters away from the second dark fringe. Let's recall the formulas for bright and dark fringes. For bright fringes, Ym equals m lambda L over d, where m is the order number. For dark fringes, Yn equals n plus 0.5 times lambda L over d, where n is the order number. Let's write expressions for the positions of the fifth bright fringe and second dark fringe. For the fifth bright fringe, m equals 5. For the second dark fringe, n equals 2. The difference between these positions is 4.13 millimeters. So Y5 minus Y2 equals 4.13 millimeters. This simplifies to 2.5 lambda L over d equals 4.13 millimeters. Now let's substitute our known values. L equals 1 meter and d equals 0.5 millimeters, or 0.5 times 10 to the minus 3 meters. Solving for lambda, we get lambda equals 826 nanometers. This wavelength corresponds to red light in the visible spectrum, which is a reasonable result for a Young's double-slit experiment. Let's solve a problem involving 3 capacitors connected in parallel. We'll find the total capacitance and determine the charge on each capacitor when connected to a voltage source. Here's our problem setup. We have 3 capacitors with capacitances of 2 picofarads, 3 picofarads, and 4 picofarads connected in parallel. We need to find the total capacitance and determine the charge on each capacitor when connected to a 100-volt supply. Let's draw our circuit diagram. Here are our 3 capacitors connected in parallel. The first capacitor has 2 picofarads, the second has 3 picofarads, and the third has 4 picofarads. And here's our 100-volt supply. For capacitors in parallel, the total capacitance is the sum of the individual capacitances. So, our total capacitance will be 2 picofarads plus 3 picofarads plus 4 picofarads, which equals 9 picofarads. Now, to find the charge on each capacitor, we'll use the formula Q equals C times V, where Q is the charge, C is the capacitance, and V is the voltage. Let's calculate the charge on each capacitor. For the first capacitor, Q1 equals 2 picofarads times 100 volts, which equals 200 picocoulombs. For the second capacitor, Q2 equals 3 picofarads times 100 volts, giving us 300 picocoulombs. And for the third capacitor, Q3 equals 4 picofarads times 100 volts, which is 400 picocoulombs. Let's summarize our results. The total capacitance of our parallel combination is 9 picofarads. The charges on the capacitors are 200 picocoulombs on C1, 300 picocoulombs on C2, and 400 picocoulombs on C3. Notice that the total charge is 900 picocoulombs, which equals our total capacitance of 9 picofarads times 100 volts, Let's solve a problem involving two cells connected in parallel. We have two cells, one with EMF of 2 volts and internal resistance of 1 ohm, and another with EMF of 4 volts and internal resistance of 2 ohms. These are connected in parallel across a 10 ohm resistor. Let's draw the circuit diagram. Here we have our first cell with EMF E1 and internal resistance R1, and our second cell with EMF E2 and internal resistance R2. Both cells are connected in parallel across this 10 ohm resistor. To solve this problem, we'll use the concept of equivalent EMF and equivalent internal resistance. 4 cells in parallel. The equivalent EMF is given by this formula. E equivalent equals E1 times R2 plus E2 times R1, all divided by R1 plus R2. Let's substitute our values. We have 2 volts times 2 ohms plus 4 volts times 1 ohm, all divided by 1 ohm plus 2 ohms. This gives us 8/3 volts. Next, we need to find the equivalent internal resistance. For parallel connections, the equivalent resistance is given by R1 times R2 divided by R1 plus R2. Plugging in our values, we get 2/3 ohms. Now, we can simplify our circuit. We have an equivalent cell with EMF of 8/3 volts and internal resistance of 2/3 ohms connected to our 10 ohm resistor. To find the current in the circuit, we use Ohm's law. Current equals EMF divided by total resistance. The total resistance is the sum of the equivalent internal resistance and the external resistance. This gives us 1/4 ampere. Finally, to find the potential difference across the 10 ohm resistor, we multiply the current by the resistance. This gives us 2.5 volts. Therefore, the potential difference across the 10 ohm resistor is 2.5 volts.